So the next talk in this session is from Joseph Tassarotti from NYU, and it is on verified density compilation for a probabilistic programming language.
It just worked before, but yeah. Let's see. Thank you. Okay, yeah, thank you for the introduction. So this paper is part of a larger project in which we're trying to build a verified compiler for the Stan probabilistic programming language. We're calling this compiler ProbCompCert because it connects down to CompCert for end-to-end guarantees and because we're not very creative with our naming. So this paper is describing just a portion of the verification. We give a mechanized semantics for a subset of the Stan language, and then we use that semantics to verify a subset of passes in a component of the compiler called density compilation. So in order to explain what density compilation is, let me give a little bit more background on Stan, our source language. So Stan is a language for doing Bayesian statistical analysis. Let's imagine that I wanted to analyze a data set of 100 coin flips and try to make inferences about the bias of the coin. So on the slide here is a simple Stan program that will help me do just that. I start by declaring the format of the data that I'm trying to analyze, here saying it's an integer array of 100 flips. Then I declare the unknown parameters I want to make inferences about. Here, mu will be the bias of the coin. So I specify that it's a real number constrained to lie in the unit interval 0, 1. And then finally, I have the model block, which is the heart of the program. It specifies a probability density function that connects the parameters and the data. So I start by giving what's called a prior distribution on the parameter mu, postulating that it was sampled from the uniform distribution. And then I specify that each of the coin flips in my data set were independently sampled from a Bernoulli distribution with bias given by mu. Okay, so now given this model and some observed data set of coin flips, in the Bayesian paradigm, what I'm supposed to do is go back and update my prior beliefs about mu to the so-called posterior distribution. All right, but it turns out to be intractable in general to compute the posterior distribution. So what a compiler for Stan is going to do is it's going to generate a binary that will help me compute an approximation of the posterior. So how does it help me approximate the posterior? It uses an algorithm called Markov chain Monte Carlo sampling, which we just heard a question about. I don't have time to explain how MCMC algorithms work. I just want to say something about what they impose on the structure of the compiler. So in particular, in our compiler for Stan, we actually have two separate compilation pipelines. One pipeline emits something called the density function. This is a blob of code that computes the probabilities given by the model block. And then a separate phase emits something called the proposal generator. The details of that aren't too important here. What happens then is that those are linked against a runtime that implements this algorithm for generating samples in a big loop. Okay, so in this talk, I'm going to focus on the pipeline that gives us the density function. That's what I mean by density compilation. All right, so what's our specification for this verified density compiler? Well, we heard a nice description in the previous talk, right? The canonical notion of correctness for a compiler, if we think of it as a function that translates between languages, well, we'd expect it to preserve or refine the behavior of source programs. So we want the behavior of compiled programs, here C of E, to be a subset of the allowed behaviors of the source. Okay, so what are the behaviors or the semantics of these Stan programs that we're supposed to be preserving? So in this project, we give kind of a hybrid or two-level semantics for Stan programs. We start with an operational semantics that's given in small step style, which explains how you compute each of the expressions and statements we saw in the model block. This is kind of similar to CompCert's C-Lite semantics, if you're familiar with that. And then on top of that, we define a denotational semantics, which from the density function given by the operational semantics gives us a probability distribution. Okay, and so this is similar to a pencil and paper semantics of Stan that Goranova et al. Gave in their Popple paper a few years ago. So digging into the details a little bit, the key on the operational level is that the model block is computing a probability density function. So on the left here, I've got the model block from the example program that we started with, and on the right, I've got a desugaring of that program that makes this density calculation clearer. So in Stan, there's a special reserved variable called target, which at the end of the model block is implicitly returned. Okay, so the idea of this special variable is that it's going to accumulate the probability density calculated so far. And for numerical efficiency and stability reasons, it actually is going to calculate that probability in log space. So the idea is each time that in the program on the left we had this sampling statement with the tilde, operationally what's going on is we don't generate some fresh sample. What we actually do is we calculate a log probability according to the specified distribution, parameter, and observed value, and then we add that log probability to the running sum in target. Okay, so even though the program looks like it has this randomized behavior, what's going on is the model block is actually specifying a deterministic function that tells us how to compute probabilities. So then on top of that description of how to compute probability densities, our denotational semantics defines a probability distribution representing the posterior on parameters. And it turns out that the density only specifies things up to normalization by a constant. So what we do is we say that the obtained probability distribution P here will assign a probability to some subset of parameters A in proportion to the integral of exponentiating what the model block would calculate. All right, and so it's proportional to, because in a separate pass we normalize so that the probability sum to 1. So this is purely a semantic device. It's not like we're actually computing this integral. It's just the meaning of the program. And the idea is that the density compiler should preserve this distribution through all the layers of compilation. Okay. So how do we prove the correctness of the density compilation? Well, the first idea is to take inspiration from prior work on verified compilation and break compilation up into a series of very small passes between well-defined IRs. Okay, so here I'm showing the pipeline we're using. You'll see it bottoms out at CompCert C-Lite, and then we switch over to using vanilla CompCert to get down to assembly. And then I've highlighted here in yellow the 3 passes that we've verified. So why those 3? I mean, it's a little self-serving, but the reason is that I think those are the 3 most interesting in the sense that they actually involve probabilistic reasoning. The rest are kind of classic compiler passes. Okay, so that breaks the problem down into smaller pieces, but there's still the question of how do you verify each of those passes? Okay, so our proof strategy mimics the structure of our semantics in that we start with an operational proof and then we switch over to denotational arguments. So on the operational proof, we use forward simulation, like you're used to if you've looked at CompCert's proofs, to show that the compiled model block, C of model, what it computes is some mathematical function G applied to what the source model block would have computed. Okay, so basically we recharacterize the syntactic transformations the compiler is doing into some more abstract mathematical description. And then on the denotational side, well, we want to argue that that integral we were looking at before is proportional to the source integral. Okay, so since we gave that recharacterization in terms of this abstract mathematical function G, now this part of the proof is just, reasoning about integrals. So you dust off your freshman calculus textbook and, try to remember how you prove things about integrals. So let's look at an example for one of the passes that we've verified. So an important component in density compilation is a pass called reparameterization. The idea here is that Stan allows the parameters to have a constrained range. So we saw an example of this in the beginning program. So I can specify that a parameter either has a lower, upper, or both lower and upper bound. It turns out, for various reasons, that the runtime doing the sampling actually wants to operate or sample over an unconstrained space, okay? So it's the compiler's job to bridge that gap between the constrained and unconstrained representations. So concretely, if we have a parameter alpha with a lower bound of b, then what's going to happen is the runtime is going to sample some unconstrained value, call it alpha prime, that's an arbitrary real number, and then it's going to pass that into the model block, and the compiler will have replaced all the uses of the original constrained alpha with instead an expression that computes the exponentiation of alpha prime plus b. Okay, so if you think mathematically, that remapping gives you a value that lies in the interval from b to positive infinity. Okay, so that's, a little unusual for a compiler to do, but I guess it's just some kind of remapping of variables. But now here comes the very strange thing, which is that the compiler also inserts an extra statement at the end of the model block to add an additional value of alpha prime to that running target variable. Okay, so the first time I saw this, I thought, well, that makes no sense. How can that be semantically preserving? You just added in an extraneous addition. The solution is that operationally you've changed the behavior, but if you think about the denotational semantics, right, this remapping that the compiler is doing is analogous to doing a change of variables in an integral. And again, if you remember that freshman calculus, when you do a change of variables, you have to scale the integrand by the derivative of the remapping that you've done. So since we're working in log space, multiplying by the derivative amounts to adding the logarithm of the derivative. And so the derivative of that transformation, exp of alpha prime plus b, when we take the derivative and the logarithm, that amounts to just adding alpha prime. Okay, another transformation is called additive constant optimization. So this is a generalization of a transformation that the reference stand compiler does. The idea is we look for any statements in the model block that are of the form target plus equals some function plus some extra constant c. And the idea is this optimization drops the addition of that constant c. Okay, so we just replace it with target plus equals f. Okay, so once again, that is very strange if you're used to a normal compiler, right? For us, we would only drop that constant if c was, say, 0. So why is this okay? Well, again, the denotational semantics says that the probability distribution is only defined up to normalization by a constant. And so if you imagine if our original program, if its model block was effectively e to the model times some constant, plus some constant d, right, then that amounts to scaling the integrand by e to the d, and since integration is linear, when you normalize, that coefficient is just going to cancel out. Okay, so once again, you've changed the operational extensional behavior of the model block, but you've preserved the underlying probability distribution that it represents. Now, I would be remiss, but there's one caveat here, which is, of course, that you need to check that the target statement you're executing does not have some implicit dependency on a variable value, right? So if I have a control flow dependency on some quantity x, then even though c is a constant, whether we execute the statement may or may not be constant valued, so it's not safe to drop the constant c here. And it turns out that in trying to prove this and reasoning about this issue, we realized that there was an error in the Stan language reference manual where they basically implied that it's always semantically preserving to drop these kinds of constants. Okay, so now I need to mention one important limitation, which has to do with the sad fact of floating point numbers. So the denotational arguments I've been describing here implicitly assume that you're operating over exact reals, but sadly, of course, on our finite computers, we can only handle approximate floating point arithmetic. So we're not doing integrals, right? We rarely have something that's more of a discrete sum, and we have the issue of round-off error. So what to do? Well, the, I guess, very principled thing would be to try to say, well, we don't have perfect semantic preservation, we just have some kind of approximate preservation, and we could try to analyze the error and bound it. But that's too hard, and I have no idea how you do that, and I'm not even sure you can prove some generic approximation theorem. So in practice, what we've done is we've given up, and for the purposes of these denotational arguments, we treat things as if they are exact real arithmetic over, an integral that's going over arbitrary space. So this is a limitation because it means our correctness theorem is conditional, right? It's up to errors introduced by roundoff. On the one hand, that's too bad. On the other hand, in some sense, that is the kind of idealized model that the Stan language developers are operating under. I mean, when they write down these descriptions of compiler passes, that's kind of what they have in mind. Certainly, they're aware of numerical roundoff and they try to minimize it. But in terms of the abstract semantics of the language, I think this is about the best you can do from a formal perspective. Okay, so to conclude, we have a mechanized semantics for a subset of Stan in the Coq proof assistant. We've verified a subset of passes in this component called density compilation. And the proof technique involves this kind of interesting hybrid operational and denotational approach. And with that, I'm happy to take questions.
Hi, Jackson Mayo from Sandia. A couple of questions. With the reparameterization you do for bounded parameters, it seems an alternative would be to change the proposal distribution so that you never go outside the allowed range. Do those differ in performance or provability?
Yeah, that's a great question. So rather than changing the model block, you could try to make the sampler respect the constraints. I think it imposes harder engineering challenges on the proposal generator, and in particular, Stan's proposal generator is very sophisticated. So I think from an engineering perspective, it's better to do the reparameterization on the model block code. Yeah.
Okay, and my other question for Stan and for your proof approach, is there anything that really is specific to the fact that these are motivated as Bayesian models versus, really this is just an instance of conditioning? It could be conditioning any probability distribution. And so would there be use cases of interest that are not driven by Bayesian models?
Yeah, I mean, we're taking advantage of some restrictions that Stan has, right? So the structure of the language means it really is decomposed in this just compute a probability in the model block. There's not kind of an arbitrary observe. Another trick we're playing is that parameters in Stan are continuous, so we can give semantics in terms of just Riemann integration. We don't need full-blown measure theory. So I think some of these ideas could be applied, but we are right now exploiting some limitations of Stan.
Thank you.
Hi, my name is Stephen. Nice talk. So my question is about kind of the choice of verifying directly on the Stan language, right? Which is quite surprising, right? It's building this, it's working in the log domain, it's adding things to logarithms. So I'm curious if you considered an intermediate language that is nicer in a lot of ways, has more structure, doesn't work this way, and then give a semantics preserving translation into that and then reason on that. Or I'm curious for your thought process there, kind of, or maybe, what you would do differently maybe now that you've gone through with it. Anything like that would be super interesting to hear about.
Yeah, so I mean, we do have an intermediate representation that we call Stan Light that cuts out some Stan features, but it's still pretty faithful to Stan in some regards. I think it is interesting to try to come up with some kind of general target so that you could have different things and kind of reuse some of the verification burden, but I haven't thought, I think that's a hard problem to come up with the right architecture for that. Yeah.
Thank you.
Yep.
Hi, this is Django Lee from Quest. I had a question about the limitation with regard to floating points. So you mentioned that currently floating points is somewhat of an unavoidable discrepancy between the ideal and realistic. However, there also exist techniques for exact real arithmetic, and have you considered incorporating them into your development, or would that result in a compiler that is too slow?
So that's a great question. Yeah, so could we use exact real arithmetic? I really want to do that, so that's what I'd like to look into next. So as far as I know, most of those exact real arithmetic libraries don't necessarily have built-in support for exact sampling over, continuous distributions, but I think you could define that and you could work with that. And then it's just a question of how efficient is it, yeah.
All right, thank you.
Let's thank the speaker again.